All right. So I've got an echo in the back there.
Turn off your speaker, please. Turn off your audio.
I'm being blamed for it.
Yeah, you need to just turn off your audio now for the Zoom. Or from your computer, yeah. You need to generally mute.
Yeah, muting. That should be me off.
Good.
Okay.
Okay, back to the screen.
We found the culprit. It was me. All right. So this really should be an ArduPilot guided mode discussion and a quick little control update at the end that Bill asked me to do. Now, I apologize in advance. I had set myself a goal this year of not going over time. And then Bill sent me an email, or sent me a message saying, look, I'd really like you to just discuss this at the end. So I'm going to rush through and hope for the best, but I have a reputation and I'm afraid I'm going to probably live up to it. Sure. All right. So my motivation for this particular talk. We get a lot of, like, we not so recently anymore, did a bunch of guided mode updates where we made much fuller use of the message, and the messages are actually designed very well and very cleverly with a lot of foresight into what you might want to do. And until you start really trying to understand what they're doing, I didn't really appreciate why they're so powerful until I started looking at it and go, well, how is this designed to be used? And then I started to realize the cleverness behind the design of those messages and how flexible those messages, how much flexibility those messages give the users. Recently, we went from a situation where it was really, we just want to try and support these messages. And, we've been doing this for a lot of years, right? When Randy and I first started talking about doing this, and Randy wanted to give people an option to use these guided messages to move stuff around. It really was, okay, what can we do to make this happen? And this is back when, waypoint navigation was still getting developed, right? And so we just needed to give the people something to start this process. And so it really was just a position go to here sort of thing, and it worked, right? Now we have moved from just a position go to here and we get there to being able to specify simultaneously position, velocity, and acceleration. I want to try and explain in this presentation what that means and how that's used. So when people come to use it, they have a better appreciation of their potential and why their first sort of attempt is perhaps naive, and their initial ideas of what they think we should have done are naive. And it's much more attainable to actually move to those next levels of control, and why their initial thoughts have problems, and explain where those problems are. Now, the other thing that we've done recently, very recently, is Takeoff. Up until the last release, we didn't explicitly handle the transition between being landed and not being landed, so that when you're landed, you are restrained by that ground, and we all know when you're restrained by that ground, you can tip stuff over, right? And copters do nasty things, and depending on your ability to control attitude, you either drag furrows in the ground or you drag propellers in the ground, right? So it's either landing gear or propellers. But most people, it's the propellers. So now we explicitly handle this thrust ramp up and a detection of that transition between being landed and not landed, in which case we release all our position controllers when we're no longer in contact with the ground. And so it's created a much safer takeoff, and it also allows us to explicitly handle the ramp up transition and how the aircraft behaves through that mode. So I'm very happy with that. It makes me feel a lot happier when I look at aircraft taking off. And it takes out that, oh yes, we're okay, sensation every time somebody takes off. Some of the future stuff that we're looking at with the controls is the six-DOF architecture, and that's what Bill's asked me to give a quick, more detailed summary at the end of this presentation. Currently, the other recent changes, we've added an offset in the position controller that we use to do surface tracking. So it allows us to have a nominal position and then provide an offset, and we're able to then surface track using that offset, using a lovely kinematic transitions through these offsets that doesn't create sudden spikes through our controllers, and to use low update rate data to create these smooth kinematic paths. We want to extend that to X and Y so we can have an EKF reset, EKF lane switch with a position offset, and then use that kinematic path to smoothly change onto, so one EKF thinks we're here, the other EKF thinks we're here. If we switch from here to here with an EKF lane switch reset, the copter goes, oh, shit, 2 meters off to the side, and it jumps across. I want to go, oh, we're 2 meters off to the side. We'd better just move across then, nice and without scaring the crap out of anybody, right? So, and we can set that kinematics to make it, however, like whatever aggressiveness we want that to be, right? The other thing I'd really like to do is, and I know Pete Hall's right with me here, I'd love to see some the SITL models enhanced, at least for the multi-rotor, to account for a motor model, a momentum model of the propellers, and a basic thrust model of the propellers. We've got some of it in there, but it fundamentally means that you can't do a proper yaw tune and a multi-rotor in SITL, and there are a lot of effects that just aren't accounted for. What's that? Okay, I think we're going to have lots of takers on that. Everybody knows that I'm not the programmer of the dev team. I'm the sandbox person, but yeah, it's something I'd love to sort of see happen, and I would love to be able to provide like levels of aircraft in SITL, like levels of models, so that when we're doing our check, we can have the poorly tuned first timer aircraft, so we can sort of say, yes, we want to make sure that this particular code works on a poorly tuned aircraft, you know, because that's where we think the risks are. And we want something that doesn't really follow the track, you know, flies like a plane. Then we want other stuff where we actually want almost an idealistic model, because that's not what we're testing. We want to make sure that precision landing lands on the target with a well-tuned aircraft. We don't want to be trying to tell the difference between something that can barely hold thing, or it's got some oscillation in it, and the quality of our precision landing code, or that change, to help reduce those flapping tests and that sort of thing. All right, guided mode. So there's lots of flexibility in these messages, and this is something that people really don't understand, is why that flexibility is there and what it gives you and what not using it takes away. So we've got position and velocity, or position and velocity and acceleration. You can just provide acceleration, velocity, or velocity and acceleration, or just acceleration. And then at the heading, you can have a heading, or a heading and a rate, or just a rate. And depending on what you're trying to do, you might use different commands, and you can switch between these commands depending on what you want to do. You might say, oh, I want to rate track this thing, and now I want to look back here. I don't care how you get there, I just want you to look here. And so you can give a rate only command while you're tracking this thing if you want, and then you can give a heading only command if you just want to look over there. If you want to look at a very specific heading that is changing by a known rate, and you want to know that you're right on that thing, you give a heading and a rate. And so, and I'll show why each of these things are important, and why you can't just give a heading if you're trying to track something that's moving if you want accuracy. This is sort of the heart of my talk here. I think when users are doing this for the first time or early on, they have a misunderstanding of the amount of information that they're providing, because in their minds, they know what they want. And what they want is simple. And it is truly simple. The problem is the amount of information they're providing is a lot simpler. And there's that lack of understanding of that contradiction. And they see these effects and they don't like them because they shouldn't be there. But unfortunately, we can't read their minds and we can't look into the future. So first thing that people don't understand is that your commands are not possible. Okay, you define discrete commands. We do not have a teleportation attitude controller that can jump you from here to here in an instant, right? We have to move from here to here, which means when you tell us to do something, we can't just do it. We have to work towards that goal of complying with your command. Because it's discrete, you're providing your commands once every second. We have to fill in the gaps. There's 400 of our time glimpses that we get to make a decision that we need to fill in between your commands if they're coming in every second. Okay. Then there's where we don't have the teleportation device here. We have a very real aircraft with very real limits that we need to respect as we're trying to comply with your wishes. And those come into two parts. One of them is the physical aircraft limitations, the absolute physical limits. And then there's the parametric limits to which the user has said these are the safe limits within the aircraft's limits that you can access. Hopefully you're told those limits are within the aircraft limits and not outside. But in which case we start getting some problems. And thankfully we sort of handle those reasonably elegantly, but that's more difficult again. So the simple example of set position target. You can see when you look at this, there is a huge number of options here that you can choose from, and combinations of data that you can send in. And as you ignore different parts, we don't allow all combinations of ignore, obviously, or perhaps not obviously, but basically we allow you to ignore. You can only you need to keep, if you can't have position and acceleration and ignore velocity. Basically, you can't ignore the middle ones, right? But you can do a position, velocity, acceleration, a acceleration only, a position only, a velocity only, but you can't do position and acceleration with no velocity, right? An example to try and illustrate how little information we have. You provide an angle command, just a heading, your heading. We have an angle. What do we do with that? Okay, now we sort of have an assumption that we need to get there. And this particular graph sort of says that, you know, you're moving that particular direction anyway, and so we can smoothly sort of get to that angle and stop. But the idea is that, okay, this is an angle. We've only got this angle, so it's reasonable to assume that we want to hold that angle, right? That's what, you know, we've only got one data point, so let's hold that angle. But then 10 seconds later, we get another angle. Now, what does that mean? Now, tell me what the user wants at this point. It's hard to say. Now, for the last 10 seconds, we've assumed we're holding that angle, but were we right in that assumption now? Now, what the user wants is the magic teleportation device, often, that instantly takes us to that new angle offset. But perhaps the user's a little bit more reasonable, and he expects a nice slew to that angle. But that's not possible, all right? So we can't do that. We might be able to do a nice acceleration curve to that angle. So is that what the user expected? Maybe, maybe not. Maybe the user is actually starting to turn and it wants a continuous thing. Maybe they're speeding up to rip around and they want to do a 360-degree turn. Maybe the user is following a particular target and wants you pointing at that target because that's when it read it. So it actually wants you to already be there at that time. And so you can see when people are just providing this very limited amount of information, it doesn't fully describe the range of things that you may want to be doing. So we can only act on the commands we receive. We can't look into the future. Now, there's a little thing here that with timestamps that I would like to sort of talk about. There is no requirement for those commands to be in any way realistic, and no expectation that we're going to receive realistic commands from the user. The command, that single position command, does not provide enough information to define a path. There's a huge amount of ambiguity there as to what that user is really looking for. And we can only execute any reaction to that command as of the time of arrival of that command. And this is where that timestamps come in that we don't currently use. It is possible that we actually could receive a command to tell us to do something in the future, which would be a powerful addition to our command handling that we don't currently do. Would cause me a whole heap of mental pain working out how to best handle that, and would perhaps require a bit of a buffer there or something. But there's a lot of potential in there to add a lot of flexibility in there. And we need, as developers, to generate a realistic path based on these commands that is achievable, efficient for the aircraft, and also pleasing. It needs to, we don't want aircraft jumping around in the sky as Yaw gets these massive commands and things like that. So we get complaints, okay? And it's generally from people that are just starting to use this and they're under a lot of pressure to get something working for their thesis or something like that. And it's, why can't I just do this? And we have to come up with an architecture that allows us to provide a broad range of capability to the user, not just cater to the simplest possible task. And sometimes that means, as a user, to do something a little bit more complicated, you need to actually put a little bit more effort into creating that information to give us what we need to give you what you want. Okay, and a lot of that's very simple, just working out what rate you want for that angular target that's moving and telling us. Okay, it's very easy to slow a rate, to slew a rate up and down along with a position and actually feed us those commands. It's just integration. Everybody did this, okay? So there's another couple of loops in your calculation that you can then feed to us, and it allows you much more power to give us what you want. And it doesn't need to be perfect. We'll smooth it out. But as I'll show you sort of as we move forwards, that, you know, it gives you a lot of extra fidelity in your commands and the response to the aircraft. So if we are following position only and we're expected to stop where you tell us the position is, we cannot be where you want us to be, okay? Because we cannot move and be at the place that we want to stop. So inherently, you must have a following error. Now, everybody that's done PID loops knows that you can add some iTerm in there and actually remove the following error. But that means when you stop, you need to unwind the iTerm and you get overshoot. We don't want overshoot. We must have following error. Now, I know we can do things with D-term and that sort of stuff, but it's always going to be a little bit of overshoot as we remove the iTerm. Now, the simple philosophy, though, that you need to understand is if you're moving that target and you expect us to be able to stop on that target, we need the stopping distance. We're going to be following by that stopping distance so that when you stop, we can stop without overshooting, okay? So when you're trying to follow a target optically by changing if you want to point directly at that target, just telling us where that target is going to mean that if you're yaw-ing to the right, the target's going to be on the right side of your frame, not in the middle where you expected it to be, okay? If we use yaw and yaw rate, you can get zero following error. And you can see now we know that we should be at this angle doing this yaw rate. And basically what I'm doing between those 2 points is I'm now integrating the position based on the yaw rate that has been commanded. So down at 10 seconds, now I've been commanded a yaw and a yaw rate. And I'm also including that yaw rate into that update. So now although it's an instantaneous change in velocity and I can't do that, so I'm going to follow behind that, but I will follow precisely at your desired attitude, your angle. But then when you suddenly stop again, I can't instantaneously reduce my yaw rate to zero in the aircraft. So you'll see this drop. Whereas when we were following the stopping distance behind, I could stop at that point. So anytime we have a discontinuity in position, velocity, or acceleration, you expect a small error to be introduced. And as you go further down the chain, those errors get smaller. Things you can do is command a yaw and a yaw rate, and then command a position with a zero velocity at your stopping distance. And we've actually used this technique early on with a lot of our navigation controllers and stuff. And it's how we actually initialize a lot of our navigation controllers. We actually work out where the stopping point is and command, okay, we're going to stop at that position. So let's command that position with zero velocity. Okay, knowing that we're not doing zero velocity now, but we can come to a stop by there. And by the time we get there, we will be stationary. We don't get overshoot. I don't expect people to be using that in their guided mode. So now in X and Y, this sort of starts to demonstrate the effect of running through a corner using different types of commands. Now, what I've done here is I've actually integrated the position and the velocity. So I'm actually just feeding a moving position in, or a moving position and velocity, or a moving position, velocity, acceleration. And we've got something that's starting at a constant velocity, goes through a discontinuity of a corner, and then comes to a stop. Now, you can see here, as soon as we hit that big discontinuity of the corner, everything jumps. But the one that jumps the least is the position only command. And that's because it's got this big stopping distance. It's got this big physical buffer that it goes through. And so that's also why it tends to cut the corner elegantly. And this is why our early navigation controllers basically used this approach to run around a navigation. We had that leash control. So this is basically simulating if you were providing positions at a very high update rate, like at full 400 hertz, or effectively, like you'd get this sort of approach if you're doing 50 hertz. When we add velocity, we don't get that following error. So we're actually following on our position because we also know what velocity we're doing. So now when we hit that corner, we're actually right at that corner. So we necessarily go past the corner and back onto the track. But because we not including acceleration, when we come to stop, that position velocity combination gets a positive error in position, and so overshoots the stopping point and comes back. Whereas you notice the one that's got the acceleration and knows it's decelerating to that stopping point doesn't overshoot that stopping point. Okay, so now obviously a sharp corner ain't that great, right? We know that that's going to cause problem. Everybody can understand that. So what about a radius corner? So radius corner, we get very similar things. So the position only 400 hertz update, really fast update, is going to follow behind. So you've still got that following error. Now, the velocity position, it has no following error, but now when it's going around the corner, it doesn't know that it's accelerating and expected to change its velocity. So it starts going wide of the corner because it's having to change its velocity, but it's not being told the velocity is changing. It doesn't know that the next sample is going to be a different velocity. So you've got this constant acceleration in this corner. So you run wide of the corner and then come back in, same little overshoot on the end. The position only, it's got its stopping distance, so it stops where you want it to stop. And the acceleration controller, because it's constantly getting this acceleration vector fed in, it knows that the velocity is changing, so it's able to follow very accurately on that corner and stop in time, like with very little to no overshoot. And so you can sort of see that depending on what your path requirements are and the accuracy of that path, depending the level of information you give the aircraft, you'll get different fidelity of your path that you follow. It requires more effort on the user side, but you get rewarded on the quality of your path. Now, there's the inescapable maths and physics of this, and don't worry, it's really simplified here. Basically, in general, your aircraft it's a little bit more complicated this with the square root control, acceleration limits, blah, blah, blah. But the distance you will follow in guided, if you're just commanding position, is going to be approximately the velocity that you move that target multiplied by whatever your position XY, like your PSC, POS XY, P value is. So you'll know that in general, you'll be following that much. It'll get a bit longer if you've got very low acceleration limits, but fundamentally that you expect at least that distance to follow behind your command for a given, if you're moving that point forwards. For a position and velocity, for a constant velocity movement, you will get zero position error. So if you're just moving a straight line generally, that'll work great for you. You'll be exactly where you want to be. But when you're accelerating, you'll have a distance or overshoot for a constant acceleration. So depending on acceleration or deceleration of approximately the acceleration that you're applying divided by the velocity XYP term multiplied by the position XYP term, right? So, so you can sort of get a direct understanding of, the tolerance you get. And you get a similar equation based on the velocity in the corner radius, how much you'll swing wide of your desired path. So if you wanted to, you could just offset your paths by that much if you wanted to, and that sort of stuff. All right. Now, thing is, we're not getting 400 hertz updates. We're getting 2 hertz updates, 4 hertz update. The faster the update, the better, right? But often we're getting a much slower update. Now, these our commands step, okay? Now, this is where the real-time S-curves come in, and people go, oh, why can't I just get the direct output? And, there's actually an argument for saying, okay, we're going to turn off our path generation and that upsampling of your path using the real-time S-curves codes, and we'll just give you direct control and let you deal with this, because maybe you know better, right? And there's some situations where and at very least it allows you to go on that understanding evolution and sort of see the problems, and you go, well, I can do it better than they've done, or stuff it, I'll just turn it on because it gives a nice curve and it's close enough, right? And I'll solve that problem myself better than I've done later. So you can see that we are getting these steps and these little jumps. Now, each time, and you've probably seen it with a guy like follow me mode or something like that, where it sits there and goes, dum, 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 or yaw as it changes heading, goes, dum, and you get, and each time you get your little oscillation because you're not particularly well tuned, because you only care about doing this follow me companion computer thing, not about tuning up your aircraft, right? And you're still running the defaults. And so every time you get a new command, it shakes and wobbles, and your camera does this, right? So by feeding this to our real-time S-curves, it allows us to remove those transients in a much more elegant way. Now, if this was a position command only, this is what it looks like. Now, this is where, it's really obvious. You get the boom, boom, like this as it moves across. And I know I'm going to regret that demonstration. But you see this thing going, every single command comes in, every single command is a wobble. It excites your controllers. The aircraft almost flips on its back, and, So
would you still see that kind of womp if the guided target was further away than you could get in the time cycle?
Yeah, so if that guided target is so far away, and this is a really good point, if you just want to go 5 kilometers over there, and you're updating that point, it doesn't matter what rate you're updating the point, your solution for that, you're exceeding you're at your maximum velocity, your velocity doesn't change. Because it's so far away, you haven't reached that stopping point. But when people are doing fine movements where they're within that stopping distance, that's where you'll see that velocity change. And if I go back, what you see here is a repeated deceleration down to that new point, right? And that's what's causing it. So now, if you do a position and a velocity command, you can see it's all smooth for the constant velocity section, but once we start going around that corner is where we start seeing those discontinuities come in. So it allows you to, so as long as the corner is not too sharp, those discontinuities won't be too sharp. Okay. And again, when we get that stopping distance, to that stop, we'll get another discontinuity on the stop. But so while we're decelerating or accelerating, we see that step, and then but constant velocity, we don't see the step. So we've sort of made it a little bit better. We've reduced the magnitude of those steps. And again, the real-time S-curves takes these low fidelity information, upsamples them, interpolates them, and smooths them out. That's the goal of it. Yep.
What happens if position and the velocities are not, they are contradictory? It means that I'm giving a position there, but I'm asking that the velocity should be here.
Then you get both things happening at the same time. So you get the velocity saying, I want to go this direction, but the position correction saying I need to go that direction. So you go this direction, right? And so then the next position, if that's the same, if you're like, if I've got a position here, but I've got a velocity here, I keep on updating a position there, and I've got a 5 meters per second velocity there, I'll initially go, well, I'm right here traveling in this direction. And it's, hang on, I want to be there still, but still, and you'll get this rubber band thing until the correction back to that position that's not changing is equal to the velocity that you're requesting in this direction.
Does it give us a velocity in that direction as well?
Well, it needs to get back to that point. Only way for me to get from here to there is to have a velocity.
Why am I asking this is for the collision awareness part of it. If my target is there,
Yep.
but there's a obstacle here. So the target is still there, but I'm giving it velocities by computing it internally so that it can curve around and go there.
Then you shouldn't be giving it the target over there. You should be giving it the path that you want to compute around.
Okay.
Right? Now, if you wanted to, and this is where those out of the box thinking starts happening, if my target's there and you want to dodge something there, you can let it just go there. And if you want to avoid something, you could give a velocity left and right and it would avoid it, and then you can let it go and it'll go back there. But you're only going to go 45 degrees each way. You can't stop that direction in that travel. If you are path planning a path around an obstacle, then you should be using the instantaneous position and velocity and telling it to go around. So you're always telling the position where you expect it to be right now and the velocity you expect it to be doing right now. And then you integrate that and you give it the next position based on the velocity that you're doing. And that way you get this nice smooth path around. You get those little steps as you go around and change direction. But when you get back into line of sight of your target and you're doing that straight line path in, all of those little steps disappear and everything's nice again.
Can I just mix it as in not with the position at all while
Yes, you can. You can say, oh, now I'm avoiding this. I'm just going to do velocity only commands, and we will integrate your position around that target, right? And then it's like, okay, now I can see my target's clear again. Just go there. I'll wait. And this is where that mixing and matching different commands we can support that, and you can change which of those in, and it will just continue to create that path based on the information you're given. And that's also where, and with the S-curves, it will also smooth it out. But if we turn that off, you'll just get what we're seeing here. And we could make that as an option. So to get better performance potential out of your path planning, you want to increase your update rate. So that's first thing, 400 hertz. You don't get, the faster you go, the smaller those discontinuities. Okay. Increase the information per message. The closer you get to position, velocity, acceleration, and a fully defined, well, given the information that's available, a fully defined path will take care of the jerk. The better that path will be. And yes, there's always a chuckle when I say I'll take care of the jerk. The purpose of the S-curves is when you give a low rate update, is to create that interpolation of those points to smooth those discontinuities out. So we turn each of those discontinuities into a jerk acceleration velocity limited S shape to offset that position rather than a step. The best way to go is to generate your theoretical ideal curve, integrate it. It can be an infinitely, like you can be using sinusoids and circles, and the absolute perfect solution. Do your integrations, work out ideally what it is, and then just feed the instantaneous values of that through guided mode out to the aircraft, and let us deal with the difference between our discrete time integration and your continuous time calculation. And that's the way to get the best performance. Yes. So, yeah. So the question is it worth providing the trajectory messages in MAVLink instead of this? So those trajectory messages are actually if you actually look at the specification of those, they are there to provide a companion computer, the aircraft's current trajectory to the companion computer, so that the companion computer knows where the autopilot is planning to go. So that companion computer can then look for obstacles along that path. And then the reply message is just one waypoint, just one guided command effectively. Now, that reply is effectively a guided mode command, which is exactly the same as what we're doing here. It explicitly says only one point gets sent back, explicitly in that documentation. And either way, it gives you no advantage over what you've got here, because you're still able to provide that entire path here. And it just means that if you want your particular curve or your corner or your spline or this type of spline or that sort, whatever you want, you can just do that path calculation that you expect. You've obviously already done the work because you've known how to convert it to a spline and represent it as 5 points. You can just follow that through and provide position, velocity, acceleration updates instantly through that single point message. So the point being that, yes, we could do exactly what you're saying and interpolate that thing, but you've already done the work, so why should we? You've got the information as that instantaneous point that you can pass to us, which is a lot more flexible than relying on us with that one formulation of spline and that one interpretation of that data. It gives you the power to interpolate that path, to interpret that path any way you want and just feed us that instantaneous data. So this is where that, yes, we could make your life really easy because you just like doing it that way. On the flip side, we could give you a much more powerful option at the expense of you doing a little bit of extra work at your end to follow that path yourself and feed that data.
The PBA solution is only kinematically consistent down to, it's not kinematically consistent when you're going around the curve, so you will still get this.
Yes, and that's the point, right? So the PVA is, every time, nothing is actually a perfect kinematic path, but that's what the S-curve kinematics do. It takes that inconsistent data that by definition is not consistent and creates a kinematically consistent result at 400 hertz. Sorry, go on.
Right, I was just saying, if the user could provide a command that represents their intended path going forward as some kind of spline, hopefully something that's, you know, infinitely differentiable, or at least differentiable down to acceleration.
And
That was the Kinematic consistent with the next one.
That's right.
You just keep the football into another.
that's right. And at the moment, most users aren't sophisticated enough to provide a kinematically vaguely consistent PVA message. So, if we get to that level of sophistication where a big bunch of our users are doing that internally and giving us this little fast update message, and that's not accurate enough, and the precise equations of those kinematic curves become well known and established in the industry, and everybody's using them, say, in ROS or something like that, then yeah, we might support that through a separate message or through that by extending this other message.
And there's another point too. There is obviously as the messaging or focus infinity, that PVA becomes 100% kinematic system.
That's right.
But what we could do if we had a definition that says that that defines that as what you're going to execute over the next DT, and DT is a known value, then we could agree on how those items are integrated.
Yep.
So there's a common expectation on both sides of the interface,
That's right.
which would probably get rid of some of the little.
That's right.
Yeah, but you're sitting at 400 foot stuff except anyway.
Yeah. So at the moment, that's not out there. So I have defined that with the real-time S-curves. It's a very simple equation. It's very efficient to calculate, and it's quite compact. It's easy to reproduce in whatever you want and type out and do your own version. And so I have defined that consistent interpretation. And if there is another one that's created that's better, hey, I'm happy to improve what we're doing, right? And get a better kinematic path based on these points. But until we get that, this is the starting point. So yeah, and the final take-home message to the people that keep that jump on, because I'm going to send forward this presentation to people that come up and ask for that simple little thing. Your easy solution will turn into your lazy solution as soon as you start wanting to do more, and you'll find that your easy solution will be discarded for a much more powerful solution very quickly as soon as you start wanting to get a little bit more fidelity into your paths. So toughen up and integrate your bloody position, right? So friendly advice to all of those first-year PhD students out there that just want to get to the end of their thesis, right? So how am I going for time?
Right, 20 minutes.
Oh, awesome. I might break my run. Any questions? Yes.
So from a Takeoff perspective, in the future we have these controls that we implemented. How does a user know what acceleration to supply if the autopilot is the one who knows all the vehicle dynamics? Are they supposed to vary those from the autopilot?
Well, you're always in this situation that if you want to move with a 100G acceleration, you're probably going to be disappointed, right? So it's up to the user to have some understanding of what vehicle they are running this on and what are the kinematic restraints of that vehicle. If a ROS thing wants to do that vehicle generically, they will need to read those limits, perhaps from WP nav limits, or we may actually have different, they will need to read those parameters, because we do list what the what WP nav lists as its limits for its navigation. And so you could safely, or you could feel confident that a competent aircraft manufacturer and tuner will set those limits for WP nav well. But on the flip side, they might set up WP nav to move really slowly, in which case you sort of go, well, maybe I know a little bit better. But having said all that, we do a lot of work inside of Arducopter assuming that we get stupid parameters, right? So we get the motor limits kick in, the lean angle limits kick in. We start, we at those points, we prevent buildup of the various integrated terms, position error, I-term error, lean angle I-term, all those things get limited. And so basically the aircraft is constrained based on its attitude limits to a point that it can catch up to your position so that by the time it gets there, it hasn't wound up so hard that it takes 10 kilometers to unwind again, right? So there are those safety nets in there in Argicopter, but you will need to pick sensible kinematic limits for that aircraft, either yourself, or from the existing parameters by fetching those parameters somehow. Yes, Jonathan.
Yes, I think Brian has a good point, and I think we could probably consider providing an API for getting the dynamic limits of the vehicle in different flight conditions.
In any case, it's something that has to be put in. It either needs to be interpreted from the existing limits of the vehicle, lean angle, acceleration, velocity, that sort of thing, or it needs to be provided by the manufacturer that's done the testing and sort of said, in these, if you detect wind of this, it's this, and some sort of equation. If somebody wants to define a set of equations or some mechanism for that, or a Lewis script for that, hey, great. That would be potentially valuable to those sorts of things, but that's outside the scope of guided mode. Guided mode's going to take your command and it's going to assume that your velocity, whether that be greater or less than WP nav,
achievable of the velocity. So if you're let's say you're commanding an acceleration north of some amount, and it's already flying.
So your maximum acceleration is going to be limited by your lean angle, subtract drag.
Yes.
Right. That's the fact of the kinematics, and that's up to your guided mode command to take that into account. If you want to take that into account, you know that you can generally brake a lot harder than you can accelerate, when you are 10% below your maximum airspeed, right?
It provides kind of a list with our capabilities to the guided mode.
It's pretty trivial to do that. I don't know, like there's no message. That's right. Like, yeah.
Accelerations, you've got lean angles. Specific forces X and Y, you've got the lean angles.
Yeah.
You get the acceleration.
Yeah, my response generally to that first year PhD student is toughen up and work it out yourself, mate. Right? It's not that hard. This is go back to your first year physics and chuck some numbers into some calculations. That's right. Yeah, look up drag on Wikipedia and work it out.
My answer is previously provided this is put it in the report. Because a lot of people are going to need, we're going to different ways around the actually have parameters necessarily, so don't get off.
Yep. All pull requests welcome.
Yeah.
It is one of those things. In loiter, for example, loiter is based on and it's, although it sounds trivial, right? Loiter is based on exactly this model of drag velocity. And so loiter is a velocity commanded, well, it's actually acceleration command that's then fed into a linear drag assumption system. And we actually did it linearly because that felt right. And we only found out a couple of years ago from Paul's work on the drag model why it's linear and not velocity squared. Right. And it was like, oh, Paul, that's why we came to that. I didn't understand why that was felt right and the other one didn't until Paul. So what's the drag coefficient on the down? Momentum drag is a linear relationship, and that's why loiter is based on a linear drag relationship. So we do have that information there. And if there was a MAVLink message that could fulfill that information, and there was enough interest from people to create that message and get it into MAVLink, the equations are really easy, but it's not my problem, right? If somebody creates that message, I'll help them do the maths to work out an approximation. But just like loiter, it's not necessarily straightforward unless the manufacturer of that drone or the tuner of that drone has gone and done those measurements to work out the drag profile of that aircraft and put it into the ECAF and fill out those parameters and that sort of stuff. So my time isn't free. These developers' time isn't free. We aren't sitting around bored, looking for something to do. We've generally got about 5 years of work we would like to improve. And it's one of those things, if it really becomes, somebody cares enough to not do it themselves and wants it part of the effort, get on the support forums, pony up some cash, and I'm sure any number of these people will do it for you. And this is the really real world. Okay, time is valuable, and if we're doing that, we're not doing something else that we think is important. So, yeah. I'm the blunt one. Okay. yeah. So I'm an engineer. I'm not a salesman. So, but yeah. All right. So, is there anything else? I'll try and run through what Bill and I are working on. Now, I suspect a lot of people will really love this. And this is what we're doing instead of creating drag messages from the WP now over MAVLink, all right? So, okay. So this, I expect this to take us another year and maybe a year after that to get it in, depending on, there are a few very talented developers that if they get their teeth into something, things happen really quickly. But with me and Bill working on it, I expect it to take a little bit of time. So not, Bill's a talented developer. I'm very much mediocre as far as getting code done quickly. So currently we have a structure for copter that assumes a single Z-axis thrust vector. We point that thrust vector by defining our attitude, and that is how we navigate. We've got a magnitude for that direct thrust vector. We have an attitude that defines the direction. So that gives us what we need to navigate. We've got constant gravity down. So with all that together, we can get an aircraft that is beautifully simple to control. And I keep on saying this, multi-rotors are by far the simplest control problem of all of our vehicles, okay? Despite being the least stable control system, once that is stable, it becomes, there's a we are spoilt with the simplicity of our control structure. Fundamentally, we've got one linear actuators and one linear. It's a 4-DOF system, one linear in the ZX body frame and 3 rotational. Now, the position controller purely works in lateral, right? It's got no rotational, doesn't need to know its position, velocity, acceleration, X, Y, Z earth frame. And it tends to output, we call it acceleration because it's normalized force, basically. But you can think of it as either the output of the fundamental output of the position controller is a force vector or an acceleration vector. single body frame Z-axis thruster, pointed using the airframe attitude, and our structure is such that the state machine talks to the position controller, gets back that requested velocity acceleration vector, and then says, oh, that's going to be this attitude, passes it off to the attitude controller with a throttle command, which is that vertical thrust vector magnitude, and off we navigate and we get great results. Now, this is what I'm about to sort of say we want to do. It gets tricky because we also have manual modes. Now, manual modes communicate with the attitude controller to provide Euler attitudes. Roll, pitch, yaw. Euler attitudes feel good to the user to use. You can do the same thing with a quaternion attitude and go the same things. And if you fly with that, and I did it the first time when I created the quaternion attitude controller, we went from Euler controller to quaternion controllers, your paths between your stick targets are wrong all of a sudden. It's subtle, but instead of passing with a perfect attitude roll, especially when you mix, you get slightly different paths and the nose dips and comes up, and things like that. So these are fundamentally different. We use the quaternion controller as a guided option. You can provide a quaternion command and a angular velocity command using guided mode to basically fly around in manual. We have the manual mode, Euler angle roll pitch with a Euler rate yaw command, which is our basic stabilize and all told. And then we have the various acro modes with different forms of attitude control in there. Now, auto tune again uses some very specific things because it's doing sudden step responses of the attitude controller. So we need auto tune to be able to talk directly to the attitude controller. But then on top of that, we have the auto modes. And there isn't much in the Euler angle roll pitch, and we could get rid of that, but it's basically thrust vector heading, right? Now, so one is using the full quaternion attitude controller. So we integrate our rates in the quaternion space and stabilize that target attitude using that. So we have an absolute calculation of exactly what our attitude should be throughout an entire acrobatic maneuver. Two, it integrates your error, so it's an error integrator, and so then we remove any of that integrated error, and so the correction paths are slightly different when you have a disturbance between those two. And the final one is rate only, so you have no corrections to the attitude, and so basically you let go of the sticks. It doesn't matter what rate you should be getting. If you're not getting that rate, when you let go of the sticks, it just tries to come to a stop, and so you'll find with the first two you'll get quite accurate rate requests all the way down, and quite an accurate rate deceleration path that's consistent with your parameters. But if your parameters aren't consistent with your aircraft, you get overshoot and some non-imperfections. Where a rate only loop, it doesn't care about those imperfections. It's just trying to go to that speed. If it doesn't get there or it goes too fast, it doesn't matter. And when you stop, it's just trying to stop. It doesn't matter where it stops. And so the rate only is much more forgiving. You don't have to have the command model and the limit set up to match your aircraft, a subset of your aircraft. So especially if you're doing extreme maneuvers that are entering into corners of your flight envelope, you see less error because you've got a pilot in the loop. The pilot's the attitude controller in acro, right? And the pilot can learn all these things. So currently, we have this thing where we go state machine, have a flight mode, it talks to the position controller, gets that data back, passes the attitude control that goes down to the motor mixer, which is a really simple thing that's really easy to understand and requires no graphs whatsoever. And out to the motors and actuators, right? And for multi-rotor, single Z-axis, roll, pitch, yaw. So, you get the idea. So, what Bill and I are proposing is we want to support a generic 6-DOF system. So what that means is that now we are able to separately define our thrust vector to our attitude. Now they may be coupled or they may not, and that all comes into the vehicle specification. So for the F-35, you can potentially have a forwards and vertical thrust vector that you can move, and you can change your actuators to, you want a thrust vector that's a little bit further back. You can actually change your actuators to achieve that while simultaneously separately setting your roll, pitch, or your attitude. For the full 6-DOF system, you can potentially use your 6-DOF controller and navigate without ever changing your attitude, and couple your 6-DOF controller to a gimbal output and just point a camera with your 6-DOF controller and have it hover around and do whatever it wants, right? A little light, Star Wars lightsaber trainer, right? Points the little laser buzzer things and moves around independently, right? All we need is the laser and the lightsaber. So the idea there, though, is we need to structure this thing because we need a separate class that defines that system. Now, quad planes and VTOLs is also another big potential user of this, right? And I need to get it done before we get 30 new frames chucked in it, right? So we need to get it mature, then do that. So we need to pass everything through the 6-DOF controller because in this sense, with Pete's 6-DOF aircraft, stabilize may not change the attitude, or he may want it to change the attitude. It just may define the thrust vector. So when he pitches forwards, it might define the Euler direction of the thrust vector, but not the attitude at all. He might have a separate little hat switch and some auxiliary functions that change the attitude, and it doesn't matter what, but stabilize is always that thrust vector, and he's just got a little light facing forwards or something, right? The trick with this is we also have, we don't want to necessarily have all of these interfaces that we have in the attitude controller in the 6-DOF controller, because we're still going to want to run auto tune, and where we're going to want direct either via the 6-DOF controller or around the 6-DOF controller to create impulses into our attitude controller to do system identification and that sort of stuff. The flight modes, things like stabilize, will probably go through the 6-DOF controller, and it's just that 6-DOF controller will decide whether to pass roll, pitch, yaw directly to the attitude controller or do something else clever with it. With the F-35, when you push forwards in stabilize, the equivalent of stabilized mode, it doesn't pitch forwards, it controls the front and rear actuator instead of pitch. Up until a point, perhaps, and then it starts leaning back. But he can define all that in those limits and add those parameters with his specific frame. So that all make sense? So, our first approach, and Bill and I are a little way down this. So, first thing is to group these existing functions and their relationships between them. We've reorganized the structure and communication paths, and currently we've just got an extension, a vehicle-specific extension of the position controller modes that handles everything below the velocity controller output. So, angle boost and the throttle control has moved into there from the attitude controller. And the acceleration controller of the vertical has moved in there. So that fast loop. We also don't directly call the rate loops in the attitude controller anymore. We call the rate loop, we call the fast loops in the extension to the position controller that then, as part of that, calls the fast rate loops. We currently got that flying on multi-rotor heli, and Bill's doing a compound heli, which has got forward thrusters, right? So those are sort of our 3 test cases. Then there's going to be a phase of begging for a bit of advice from everybody to how to actually make this perhaps a more elegant class structure that makes better sense and more programmatic sense, and more elegant, perhaps say not as, I don't know, this is above my head. Reorganize that, get that all going again. Then we'll be tempting Pete Hall to, because you get Pete's teeth into something and it generally progresses really, really quick. And he's got the fully generic example. So 6-DOF and sub, potentially blimp, a full 6-DOF potential vehicles that would make full use of this, and we can make sure all of the paths are done right. And if we can get to a point where Pete's really happy and he can do everything with his 6-DOF aircraft he wants to, we can feel confident that you can do it with most aircraft. Then we just go through that year-long iteration of, working out the stuff that you were stupid with, working out how to solve the stupid, looping around until as much stupid has been solved as possible, and then we start getting all of the quad plane stuff using it, right? So that's sort of the process that we're going to go through, and hopefully that all goes well. So part of these problems, naming everything. I don't know what the names of a 6-DOF thing versus just the attitude control of maybe there's some nice clear naming that we can get help from people. I look sideways at Paul there. Making sure that as we do this, we actually do it properly. So it's something that it's an investment for the future and not something we're going to trip over and rewrite 2 years down the track. Making sure that different control mechanisms are supported, and also making sure with the class structures and stuff that it's easy to use. Oh, 4 minutes over, I failed. So but that's significantly better than anything I've done in the past.
Start 10 minutes, you started the best of time.
Ah,
so
cool.
All good. Yeah. All right. Okay, any final questions for Leonard? Okay, so thank you very much, Leonard.